like to use the microphone for the people who are online. Anyway, I just wanted to say a few quick words of welcome. I'm Patrick Ingram, the Deputy Director of the Fields. And actually, maybe I could start by asking how many people are here at the Fields Institute for the first time? Oh, okay. How many people were here like last week? A lot of people. So maybe more of you were here for the first time last week. So anyway, I just want to say a quick word of welcome. This is sort of not really in the program, so I want to get you to your first talk as quickly as possible. But maybe I'll mention just a little bit for people who are here for the first time, a little bit of the history of the Fields Institute. There are sort of two things that I associate with the Fields Institute and with Fields, with John Charles Fields. So one of them is the 1924 ICM, so the International Congress of Mathematicians. And the story there is that this was a conference that was, the World Conference of Mathematics, but of course it had only ever been in Europe at that point. And if you know some 20th century history, in the 1920s, Europe was sort of a bit of a mess, and there was a big dispute about where to have the conference, and the French didn't want the Germans coming, and there were all these different things. But one of the people who was on the organizing committee for the meeting was a faculty member here at the University of Toronto, John Charles Fields. And he said, well, why don't we just have it in Toronto, which was probably kind of a radical idea at the time. It had never been outside of Europe. And so the story I like to tell is that, they did this. They had the ICM in Toronto. And the story I like to tell is that this was, an opportunity for everyone to sort of set aside their differences and come across the Atlantic and have this conference in a sort of neutral location. The other thing you probably recognize the Fields name from, of course, is the Fields Medal. In I guess 8 weeks or something, there's going to be another 4 Fields Medals handed out, and the Fields Medal was created by John Charles Fields in later in his life to sort of honor excellence in mathematics. Interestingly, he was adamant that nobody's name should be attached to the medal. So now his name is attached to the medal. Maybe that was a strategy. I don't know. But so those two things are sort of the inspiration, from my point of view, for the Fields Institute, which was created, I think, in 1992, is being this sort of neutral convener where people can come together in an inclusive environment and do mathematics, and also support for excellence in mathematics, as represented by the Fields Medal. And normally we have some slides and we thank our sponsors, and of course it's very important to have funding for these sorts of things, but it's also very important to have organizers. So I prefer to thank the organizers of this event. So I think for this conference, it's Yakov, Louise, Maxime, and Rita. And so I'd like to thank the organizers for putting together what looks like a wonderful workshop. I am upstairs in office 320. So if you have any questions or concerns or anything during the workshop, please come up and visit me. But otherwise, I hope you enjoy yourself. And I will hand the microphone off, I think, to Rita to introduce the first speaker.
Thank you very much. And well, on behalf of all the organizers, welcome or welcome back, whatever the case may be. And we are very happy to have as our first speaker in this workshop, Sung-Jin from Berkeley, who will be telling us about stability of the Minkowski space in the Newman-Unti gauge. Thank you.
All right, thank you for the introduction. Thank you for the invitation and the chance to present my research, the Fields Institute. It's a great honor, and also it's a great mix of audience to present this work. So as Rita announced, my talk will be about the stability of Minkowski in what's called the Newman-Unti gauge. Is the size of my writing okay for everybody, especially in the back? Right. Great. So this talk will be based on an upcoming joint work with Jonathan Luck at Stanford, who I believe was here last week, and Claude Warnick from University of Cambridge. So yeah, I guess I should say, start by saying that I apologize that for the workshop, on black holes, and I start with a talk about nothing, about no black hole, but I'll try to explain how this would fit into the larger program of what's more relevant to the theme of the workshop, but you'll have to bear with me. But as it is, the topic of my talk will be stability of Minkowski. And let me start by a review of the formulation, just to get ourselves in the mood, and also to set a notation. So when I say stability of Minkowski, I mean with respect to the initial value problem formulation of general relativity. So we want to solve the Einstein equation. So we want to think of a 3 + 1 dimensional space-time as being a solution to the Einstein equation. Let me just think about, in this talk, we'll be concentrating on the Einstein vacuum equation, where there's no energy momentum tensor on the right-hand side, in which case we can just simply write it as the Ricci curvature of this Lorentzian metric being 0. And this is supposed to be viewed as some sort of a nonlinear wave equation, for which the correct problem to pose is the initial value problem. The initial value for this problem consists of the following objects, or maybe I'll use a different letter, H and K, okay? Where H is a Riemannian metric on the 3-dimensional manifold, sigma 3, and K is a symmetric 2 tensor on this manifold. And we say that the space-time is a development, or solves the initial value problem formulation of the Einstein equation if this embeds isometrically into the space-time, and H and K arise as the first and second fundamental forms of the embedding, right? And the fundamental theorem behind this framework is the theorem of Madden-Schucker-Bruhat, and also Schucker-Bruhat, Gerard in the 50s and 60s or 70s, sorry, which guarantees that given any initial data set, there exists a unique maximal development, or maximal globally hyperbolic development, n1 + 3g. And I forgot an important thing, which I actually wanted to emphasize, that this triple cannot be a general triple of manifold, Riemannian metric, and symmetric 2 tensor, but also has to satisfy some set of equations called the constraint equations, which reads as the scalar curvature of H plus trace squared. I left too small room, minus K squared is 0, and divergence of K minus D of trace of K is equal to 0. Okay. So the theorem is that if you have a triple that satisfies this system of undetermined equations, then you have a unique development. And stability of Minkowski is a statement that if the initial data set is close to the initial data set Euclidean metric and 0 fundamental form, oh, okay. So if I, well, it's better. Okay, okay, good, good. Yeah, thanks for letting me know. Small, regular, and localized. We want to say that the development is close to the development of this, which is the Minkowski space-time. So I should have maybe, so on R3 plus 3 eta. So this would be my notation for the Euclidean metric, my notation for Minkowski metric. And in fact, we'll be asking for asymptotic stability that G sort of converges to eta to the future in some appropriate sense. Okay. So the very first thing that must be said about this problem is that it's already solved by a fundamental work of Christodoulo and Kleineman in 1993. So maybe I should start by telling you a brief review of prior works. And not only has it been solved, it's been revisited several times. And by now, there's a lot more refined understanding of this statement, thanks to many, many contributing authors. So in order to summarize some of the prior works, important prior works on this topic, let me try to draw some sort of a table. Okay, but I guess I should start by being more precise about the assumptions on the initial data. What we mean by small, regular, and localized. Okay, because that will also sort of be important in distinguishing different contributions. So basically, what you would think is that we would like to, impose that the data is small, okay, and also maybe localized. Okay, so maybe plus O of epsilon to some power in R for R large, right? And maybe because K is at the level of like a derivative of the metric, you impose that the decay for this is 1 power or faster. But immediately you run into trouble in formulating your assumptions like this, because there are actually certain rigidity that comes with this constraint equations for the initial data set. So what happens is if you just take this localization, this decay rate to be too large, larger than 1, then actually there's no non-trivial data that would satisfy this, just because of the constraint equations. So that's the positive mass theorem of Shannon, Yao, and Witten. So we have to actually add extra terms. So what we're going to do is we're going to do something like this. So I should have written the Euclidean metric here, but in the Euclidean metric, I'm going to add 2m over r, and let this m be some real number. Okay, this will actually be the mass, and this will be positive. And with this formulation, this assumption makes sense for nu between 0 and 2. Okay, higher than 2, it's subsumed by this. We'll not worry about it for now. And the the first proof of stability Minkowski is due to Christodoulo and Kleineman. In the important monograph from 1993, where they treated the case when nu was any number that's bigger than 3/2. Okay. That's a little. Is this okay? Okay. This leads me to rethink a little bit my board work. Okay. And then there's another work I want to highlight in the history of the subject of Lindblad and Newman-Unti, who introduced a different way to analyze the Einstein vacuum equation and show this proof, show the stability result. So the framework was, in this case, geometric. This was too low, right? Okay. So maybe I'll say that I'll improvise and do this. So this was the formulation, was the analysis of the Einstein equation was based on Bianchi identities. They try to understand the hyperbolicity of the system at the level of the curvature, Weyl curvature. Okay, and proceeded was the geometrically. In this approach, they introduced an approach where they can work in wave coordinates, some sort of coordinate system, where you have a nonlinear, quasi-linear wave equation for the metric components inside these coordinates, and they were able to handle data with decay rate nu better than 1 plus. This was 05. I also want to highlight the works of Bieri, which was published in 2010, and also Shen, preprint from 23, which basically falls under the same geometric approach category of crystal Kleinemann, but they greatly improved the assumption you can have on the localization. So Bieri reached 1/2 plus, and this was interesting because they were able to go below 1. Okay, and Shen reached up to an endpoint, what's believed to be the optimal endpoint, anything that's positive. Okay, and there are also other works of Hintz and Bashi, published in 2020, and I also want to mention the work of UNESCO, also there, 22, which were all based on the wave coordinates framework, but use different analyses and you prove different results. Okay. And there are many, many other works actually also contributed by some audience members here. For instance, the proof of stability in the space-like characteristic formulation by Olivier Graf. But because I'm already short on board space, I'll stop here. So at this point, since I gave you a board full of previous works that solves the problem that I'm posing, you should be asking, why are we giving another proof? So I'll try to explain that in the next part of the talk. And I should start by explaining to you how our formulation differs from the ones from before. So I'm going to explain to you the second word in my title, which is the Newman-Unti gauge. As I hope was apparent from the discussion of the tables here, it's one of the difficulties of proving this theorem or analyzing the Einstein equations rigorously in general is to find a way to deal with its gauge freedom or diffeomorphism invariance. Okay, so the Newman-Unti gauge is one way of choosing coordinates. Okay, or to address this gauge invariance. So this refers to a choice of coordinates u, r, and some angular coordinates θ1, θ2. Okay, where with the following properties: one, I want u to be null. Okay, in other words, I want constant u hypersurfaces to be null hypersurfaces, and I want the coordinate vector field dr to be null geodesic vector field. Or in other words, I want r. I want the curve where you fix u θ θ2 to be a null geodesic and r to be an affine parameter. Okay, so if you assume these, this is equivalent to saying that your metric G takes the following form. So it looks like du er plus its symmetric counterpart. Okay, it might have some function f in front of du. And then some angular metric gamma tensored with the theta a minus b, some vector field on the coordinate spheres, dA, du tensored with the theta b minus b du. Okay. So with this gauge choice, the description of G boils down to three objects: F, the angular metric gamma, and an angular vector field B. Okay. So I should comment that this gauge, okay, so this was used by Newman and Unti in the paper from 1962, but it's also seen applications in recent works in mathematical GR, such as the recent work of Chen and Kleinemann, and also Scheftel-Kleinemann. But what's different from these existing uses of this gauge from our case is that in our case we normalize the gauge a little differently. So another key word that I should explain is our center normalization. Okay, so let me try to explain how we impose this gauge, how we normalize and finally impose this gauge concretely, in a given space-time. So, and instead of writing things down, I think it's best explained if I just draw some pictures. Okay. So how we do it is we first begin by fixing a time-like geodesic capital gamma, which I will call the center geodesic, or sometimes I'll call it the axis of space-time axis. Okay. On this geodesic, I start from summation of time, and then I go for some proper time. Let's denote the proper time on this standard geodesic by u. Okay, and along this geodesic, I will parallel transport the frame, okay, orthonormal frame, okay, with one of the time-like vector being the unit tangent vector to this curve, okay. So we parallel transport this, okay. And because of this parallelly transported frame, I now have a way of assigning spatial vectors to an angle, right? So that's my theta, okay. So theta. And then, at this proper time u on gamma, in this direction theta, we shoot out a null geodesic, okay? Normalize the affine parameter so that, with respect to this, frame over here. And the affine parameter on this geodesic will be called R, okay? So all in all, my procedure would give me, union of these curves, which will form a null cone emanating from the central axis. Okay, and this is exactly how we're going to normalize the coordinates define the coordinates u, r, and theta. Okay. So an example to keep in mind is the Minkowski spacetime. So if we do this exercise in Minkowski spacetime, then without loss of generality, we can call the center geodesic to be the center of a polar coordinates, okay, in Minkowski spacetime. In that case, u would be nothing but the t minus r, the standard retarded coordinates, and r is the usual r. Theta are also the usual thetas. So these are the usual polar coordinates And in this case, F will be 1. Gamma will be the standard round metric on the sphere radius R. Okay. And B will be 0. Okay, so this is how Minkowski will be written in our formulation. So far, so good. So next, let's discuss the possible advantages of having another proof of stability Minkowski in this gauge. Okay. Of the standard normalized Newman-Unti gauge. So the first advantage is really what goes back to the paper of Newman-Unti, where from which we get this name, which is that the analytic structure of the Einstein equation is particularly simple. Okay, in this gauge. So what happens is this. So in this gauge, it turns out, if you know the information of certain extreme components of the Weyl curvature, which is exactly the curvature tensor in this case, because the Ricci curvature is 0, namely the component angular dr, angular dr. Okay, and remember dr is the null geodesic vector field. In this picture, it's clear that the dr vector field will be the outgoing null vector field that's tangent to these cones, right? Okay, so what Newman-Unti observed was that with this gauge choice, once you know alpha, these particular components of the curvature, then you get to determine all other geometric quantities. Which include other curvature components, Ricci coefficients. So the coefficients inside the covariant derivative, and also the metric coefficients. Okay, by a simple procedure that only involves solving some transport equation along the dr direction. And in this case, we're implicitly using the center normalization, because the normalization at the center gives us the boundary data or the initial data for this transport equation. So in this gauge choice, I can integrate everything from the center, okay, and recover all the geometric other quantities if I know alpha. Or let's say boundary value given by center normalization. Okay. Furthermore, alpha by itself, at least at the linear order, satisfies. Mm-hmm. Sure.
The way you say this, are you suggesting that's not true until we know? I assume you allow loss of derivatives.
Yeah, I allow loss of derivatives. Just from alpha, I think the fact that you can get everything else, that's unclear in other gauges, but we can discuss. Yeah. But maybe here the point is that we normalize everything from the center, so there's no we're not going to consider the other null foliation. Yeah. Okay. Thank you. So at least at the linear order, alpha AB satisfies a second order wave equation. Okay, which, in honor of the topic of this workshop, I'll call the Minkowski equation. But of course, here it's really a statement about the behavior of solutions near Minkowski space. Okay. So you can imagine that coupling these could be a viable approach to the analysis. Okay, you solve a second-order wave equation to estimate alpha, and then everything else you recover by sequentially integrating transport equations from the center. Okay. So the second advantage I want to point out is that this is well suited. This gauge turns out to be well suited for global symptotics. So as you'll see pretty soon in the more precise statement of our theorem, our proof already gives a proof of almost sharp Bondi-Stokes peeling for suitably strongly asymptotically flat data. Which goes beyond what's proved in, say, Christopher Kleineman, or the work on exterior stability by Kleineman, Niccolò, and later work by Kachiota, Niccolò. The latter, okay, well, in the sense that it's proven on the whole null infinity. Okay, but in fact, there's more. Which is that the metric coefficients inherit the same decay, very strong decay, as u goes to infinity, or you can think of and let's actually in say are bounded. Okay, so you can think of sort of fixing a spatial coordinate and then sort of taking t, whatever that means, to infinity. So in that region, the metric coefficients decay as fast as how the curvatures would decay. And for instance, this is in strong contrast with what we know what happens for other gauges, such as the wave coordinates. So the wave coordinates give you a simple sort of reduction of the Einstein equation into standard form of the wave equation. But there, these behaviors would be much more slow. It's a known result of Lindblad that happens. And as a remark, let me add that by sort of the bigger reason why one might be interested in this framework is because by combining this framework with the framework of proving precise decay rates in these regions, or late time tails, that was developed by Jonathan Look and myself in an upcoming work. We show we establish the generic form of the late time asymptotics of solutions to the Einstein equation in this gauge, which is actually conforming to not the original Price's law, but a modified version of it that was that Jonathan and I proposed a few years ago. Where the curvature components, including alpha, would be decaying at a power u to the minus 6 if I just confine to a boundary region in space. And in fact, the metric coefficients, the metric difference from the Minkowski values would also converge at the same rate if I forget about the dependence of constants on R. And it is this part that I was referring to when I said that this nobody problem is a part of a bigger program, which is related to the study of what happens in black holes, and especially the interior of black holes, because establishing such generic rates of global asymptotics, in this case, in the boundary of the black hole spacetimes, is a crucial input for understanding the interior structure of black holes. And this is the first instance where we are able to verify the modified conjecture that we had on how the rate should be. Okay. But actually, I won't be this. You'll have to wait a little bit before I can tell you more about this. I'll return to stability of Minkowski for this part. Any questions so far? Okay, having discussed all the upsides of what we might have if we have a proof in this gauge, now I need to tell you what are the difficulties or disadvantages. So the first difficulty that seems to stare at you in your face when you try to analyze things here is that actually the metric coefficients, even with the best assumption on alpha, don't seem to converge to the Minkowski values as R goes to infinity, towards null infinity. So towards null infinity, or towards R going to infinity in this coordinates, what happens is that F actually seems to diverge like R. B also seems to diverge like R. And gamma there's no divergence, but at best it seems like what we can say is bounded. And this is actually, if you think about it, something that's expected. It's because we are normalizing not at future, but from the center, right? So all the transport equations are integrated from small r to large R, and therefore you don't expect these to have good decay. Let me just complete what I was saying. Even if alpha were any let's say u prime with nu large, this seems to be the best you can prove. And in fact, I think there's a sense in which that this is actually the generic behavior. So that's the first difficulty. So you analyze the consequence of this first observation, and you realize that, okay, towards R goes to infinity, you have not even convergence to the Minkowski values. Second difficulty is the presence of the center. So alpha is necessarily not smooth. near at r is equal to 0, because the vector field dr that's in the, for instance, dr that's in the definition of alpha, is only Lipschitz, right? So somehow, this is another difficulty that you deal with, that you have the issue of center. And finally, last but not least, if you're an analyst, you should have asked this question, at the very beginning, which is that there's possible loss of derivative issues. Because when you solve the transport equation to get other metric coefficients, you don't gain any derivatives, and you might worry that you have to worry that when you plug this back into the analysis of the wave equation, you have a losing scheme, right? Okay, but the main punchline, I guess, is that all these difficulties are okay, and we can prove a theorem. So let me tell you the theorem. Okay, so I want to reuse this board. So this is theorem. We're going to consider, so our proof, in fact, actually would include all the entire range of mu that was considered in this table, and a little bit more, in the sense I'm going to explain. So we're going to be allowing mu, the decay exponent, to be anything between 0 and 3. Okay, so 0 corresponded to the result of Shen, the optimal sort of slow decay rate, and 3 is, I guess, the very, very strongly asymptotic initial data. Okay, and in this case, I need to modify the ansatz for the initial data, where I need to add in more terms in the expansion. So here, I need to add in a term that's like 1 over r squared. Okay, and here I need to introduce the effect of the angular momentum. R, I think, to the power 4 dxj, and then there's a symmetric term that I'm not going to write. Okay? So there are two justifications for putting in terms like this. First thing I should say is that you need to put in a term like this, again in view of the rigidity of the Einstein constraints. Okay, so these force you to have certain slowly decaying terms in the data. So if you want mu to be larger than 2, then you need to add in terms like this. There's a big freedom of what kind of terms you want to add, but this is in some sense canonical, in the sense that this is the expression of the gravitational field from far away of arbitrary matter distribution with mass m and momentum j. And also another way that might be more familiar to you would be that this is the Kerr metric written in a strange coordinate in the center of mass frame. Okay. Anyways, so our main theorem says that stability Minkowski holds for in the center normalized Newman-Unti gauge for this range of decay exponents. Okay, and we have further statements about the behavior of the solution. For instance, as r goes to infinity, we can say that alpha behaves like epsilon. Epsilon is the size of the data to the power minus mu 2 minus mu. And other components of the curvature, let me not write, but you can easily derive what they should be using the transport equations. And let me say that U is equal to 3 corresponds to Bundy-Stokes peeling. So 5 for alpha, 4 for beta, if you know what that means, and so on and so forth. Okay. So by almost peeling, we mean we reach almost 3. Okay. So as U goes to infinity, the curvature distinction between curvature components don't really matter. So I'll just write curvature. This we show decays like, okay, so there's a funny a loss that we allow for, the non-smoothness like this. But other than that, we have decay in U. That's, I guess, whatever should add up. So that's minus. Don't worry about these small signs. I need to put delta, a small factor of delta here, but you don't have to worry about it too much. The point is we get, also a convergence, towards Minkowski in the sense that curvature, goes to 0 in this quantitative sense. And actually, for the third statement, let me return to here. We are able to refine the estimate on F. So under these assumptions, over there, F will in fact, we'll have this growth, but then we'll have decay in U. That's like -1 minus mu. In particular, this is integrable. B would have a similar behavior. And gamma would converge to the round metric at some rate. Okay, so that's the main theorem. Any questions?
The level of the data when you wrote to that big O of R,
Mhm.
I assume it's like not equal to the explicit times R more or less. I mean, or not explicit, but like there is a function.
Right. So actually, in the context of the stability proof, we'll only care about the upper bound. Yeah. But actually, in the work in progress on the latent tails, we identify a generic profile in front of this, which shows that generically, actually, you would see this growth behavior in this gauge. Any other questions? Yes, Hamid? Yeah, with this normalization, yeah. Yeah. No, right, yeah. Okay, how much time do I have, Rita? 10 minutes, oh wow, okay. That's a lot of time. Maybe I can tell you the whole proof. And maybe this can also go up. Okay, so now in the remaining time, I want to discuss the ideas of the proof, and I want to say at least a little bit about how we resolve each difficulty that I listed over there. Okay. So let's start with difficulty A. In order to discuss this, we need to write down the equation that's satisfied by alpha. I'll do that. I'll keep only terms up to linear order. That's actually where, pretending that we're on a fixed background whose metric is given by this. Okay, that's where you already see the main analysis. So the Minkowski equation for alpha is the following tensorial equation. I'll write down these things first and then explain what these mean. So for algebraic reasons, not very serious, we're going to be working with r squared alpha. Okay. In particular, this you should think is at the level of the metric in terms of scaling. So that makes it a bit easy to think about things. There's 2 squared alpha, r squared alpha. So these are the linearist terms around this background, and I'll put everything else on the right-hand side. Okay. Now, so these are certain derivatives in the directions E4, E3, and E4. E4, this is going to be the a null frame. Okay, that's adapted to this coordinate. E4 is the dr vector field. It's the outgoing null vector field. E1 and E2 you can think of as just the coordinate vector fields. Okay, and E3 would be the unique null vector field, which is orthogonal to these tangential angular directions, and is normalized with respect to E4. Okay, its inner product should have -2, and if you just compute what it is, can I remember what it is? So it should be something like this, I guess 2 minus f dr. Okay, and these derivatives are nothing but the projection of the usual covariant derivative to tensors on spheres of constant u and r. You see, alpha is a tensor field is tangential to each SUR. It's a traceless symmetric 2 tensor on each sphere. Okay, so I want to get an equation for such an object. So every derivative I would project. Okay, so that after I take this operator, I get back an object like this, right? And yeah, this is just the angular Laplacian, okay? Formed using geometric metric gamma. Okay. So now what we're going to do is we're going to perform some estimates on this equation, and we'll be using a multiplier method, energy method, and our multiplier is the one of Mihalis and Igor, the RP method. So we multiply this equation, or contract, I guess, it's a tensorial equation, but we contract this equation by whatever I see here. Times a weight W. Oh, sorry, yeah. Is this okay? Okay, thanks. Where you can think of W as some power of R. Okay, I have to deviate if I don't want to get myself too confused. I have to deviate from the usual convention. My P won't be the P of the Minkowski, but this P would be the nu. Okay, that's my normalization. Sorry about that. Okay. So if you do it, what happens? Yeah, I sort of want to keep this picture, but okay. Let's see. So if we multiply by this and integrate, over space-time, region, bounded by 2 constant u surfaces, or maybe I only need it in the future. Okay, so I integrate this on a region which is bounded to the future by a constant u hypersurface. I'm going to call this HU. This is my center, and this is my initial data. Okay. then I get the following. So you can easily see from here that this was designed to be exactly the same as this. So when we look at the contribution of this term, we have the usual integration parts that we can do in energy estimate, right? So we're going to have 1/2 of this squared, okay? And then there should have been the E3 here, but we integrate that by parts, right? So we have this times W on boundaries, HU. By usual moves, you can take, vary the HU and take the supremum. You also get, I guess, the minus sign here because of energy by parts, the plus sign here because of my sign convention, and minus sign here, a space-time term where I see this term. But now E3 falls on W, right? Okay. And then there'll be a host of other terms, okay? Now, so far, so good, right? Because actually, we didn't see any of these difference between the coefficients, the geometry, and the flat geometry. So is this it? Are we done? Unfortunately, not quite yet, because you see, the metric coefficients do show up in one place in this board, which is the evaluation of E3. Remember, E3 saw both BU and BA, sorry, both BA and F, right? So, this is du A d theta A minus F dr falling on W. Okay. Okay, another observation. This can be eliminated by choosing W to be simply a function of U and R, right? So far so good. But fortunately, this is a term that we cannot seem to eliminate by any clever moves. So now what we do is we try to handle this. Let's decompose this into the contribution of the flat geometry, which would be just these two, which I'm going to put in the other part, and just eliminate, just separate the contribution of the difference of geometries. Okay. So the key observation, number one, is that this is essentially the Laplace-Bruniansky observation, that with a good choice of P, the space-time term that you see in this computation on flat geometry has the right sign. It has a sign that cooperates with this sign. Okay. This has the right sign for a range of P, which I'm not going to tell you the precise range, but it at least includes the range of P that we're going to use, which is from 0 to 3. Okay. Okay, so number two, how do we deal with the error? So the remaining error is now, I spent too much time on this, sorry. dr of W dV, which now I'm going to write as integral on each u, and then integral in du. So one possible strategy might be to, if you know the RP method, to try to absorb this into the bulk term that you see here. But that's not going to work, okay, because of the growth of F. But here, actually, we have a compensating feature for this error, which is that even though this grows in R, it actually is decaying in U, and decaying in an integrable way. Furthermore, it is small. Okay. So R times dr times W is roughly of size W, okay? But then we have in front of it epsilon, and then a integral factor of U, and you now look at the first term in the equation, and you realize that this is something you can just treat I Cromwell. Or you can observe it directly in this case, the way I formulate it. First, key observation towards the proof of how we essentially handle the first difficulty. You realize that this is you can avoid it like this. I'll be very brief with the other two difficulties. So in addressing the second difficulty, the idea is to realize that what we need is just some regularity of these objects in some coordinates in the smooth structure of the manifold. And in order to establish it, we don't need to actually prove the refined bounds near the center. What we can do is we can use local opposeness, low regular local opposeness of the Einstein equation, and in particular, persistence of regularity. And it's not a fancy local opposeness I'm talking about. I'm talking about something that comes from energy method. So in order to show that you can continue your manifold smoothly as a solution to the Einstein equation, it suffices to show that your H5 plus norm of your metric and H3 plus norm of your second Phonon form, K, stays bounded. And these bounds that we can prove with the estimates here are not smooth, but it's more than enough to prove such low regular bounds. So by local opposeness, we actually know that these objects are smooth objects in the background. And this smooth assumption is actually enough to justify the vanishing of the boundary terms at the center that you're going to see in this step. And finally, here, maybe one word that I can say is that here, we gain from the fact that we only analyze Minkowski, which means that we don't have to close with the same level of derivative for all components. In fact, we're going to close with the same number of derivatives for alpha and also the next curvature component beta, if you know what that means. Okay, but all the other curvature components, actually, we're going to close with less derivatives. And this is allowed because we're only looking at Minkowski, not the whole Bianchi equation. There's more decoupling, I guess. That's sort of the trick to solving the last problem. Sorry for going over time.